Welcome to my 7th video in this portfolio theory series. I would like now to look at the 3+ stock case where we have a 2 space that has mean historical returns on the vertical axis and standard deviations of return on the horizontal axis. This will be the efficient set. Okay, that is the efficient set. And bear in mind that every asset that appears on the efficient set is a risky asset. Risky asset. And now we want to consider what happens when we add in the possibility of risk-free lending. That means lending money to the federal government. In other words, buying treasury securities. And let's say that this rate right here is that rate. Okay? The rate that we receive, risk-free rate for people lending money, okay, to the federal government. This increases our opportunity set, okay. So let's just say there's a risky portfolio there, because this is a risky portfolio. I'll call it M. And this is the risk-free asset. I'll call it R. Excuse me. So if I'm at this point right here, I've got 100% of my wealth there in the risk-free asset, treasury securities. If I am there, I've got 100% of my wealth in that risky portfolio, whatever that risky portfolio might be. Okay. My axes back. There we go. And I want to show you that if we combine the risk-free asset and our portfolio M in our own portfolio that we control, we then will be able to determine the risk-return combination that we can expect to receive based on history. And the relationship is a straight line. Okay, in other words, that point right there represents half of our wealth in treasury securities and half of our wealth in this security M. It's probably a large portfolio, and like an ETF. And here we have maybe 90% of our wealth in the risk-free asset, 10% in M, and here we have 90% of our wealth in M and 10% of our wealth in the risky asset. But it's a straight line. Let me show you why it's a straight line. So we're talking about a 2-stock portfolio. So the variance of the returns for a portfolio of 2 securities, these are R and M, is the weight in R squared times the variance of the return on R plus the weight in M squared times the variance of the return in M plus 2 times the weight in R times the weight in M times the covariance, I'll put it down here, times the covariance of the returns of R and M. Okay? Well, let me just show you quickly what happens here. The risk-free asset has standard deviation of 0. Okay, once you invest in it, you're guaranteed a return, provided you hold it to maturity. So because standard deviation is 0, as evidenced by its appearance on the vertical axis, that means this value here is 0. If standard deviation is 0, then variance is 0. And that means this term disappears. Well, this term is just going to stay. There's M. This is the standard deviation of M. This is standard deviation square. And whatever weight we have in M is squared. So that term's good. Let's look at this term. 2WRWM, covar R and M. Well, let's think about the formula for the covariance of the of the returns on R and M, that's going to be equal to the sum for I equals 1 to n of Ri minus R bar times M sub I minus M bar, all divided by n. Well, it's not surprising that since the return on R is known for sure, there is no standard deviation. Remember, standard deviation is 0. If you invest in a risk-free security, that's the return that you're going to get. You're guaranteed. There's no better guarantee than the return on a treasury security. And so that means Ri is constant, which means Ri is R bar, and that means this minus this is 0. And that means every term in this series is 0 times some mean deviation. These are mean deviations. Okay? So it's 0 times some mean deviation for the risky asset M, but it's going to be 0. So this ends up being equal to 0. And if this term, since that term is 0, that means this whole term is 0. And therefore, we're left with the observation that this is equal to this. So I'll write it here, sigma square RP2 is equal to this term right here, whoops, sorry, Wm squared sigma square M. Well, let's take the square root of both sides. When we do, we get the standard deviation of the return of the portfolio of two securities is just equal to the weight in M times the standard deviation of the return on M. Well, just to make this super clear, let's see. That means, let's just say sigma RM up here is 10%. Let's just say this is 10% or 0.1. That means if I've got none of that in my portfolio, then 0 times 0.1 is 0. And then 0 would be the standard deviation of the return of my portfolio, which would be 100% risk-free asset. If I have 20% in that, then it's going to be 20% times 0.1, which of course is 0.02, and therefore 2%, which is 0.02. Let me make that a little neater, sorry. Will be the standard deviation of the portfolio's return. Portfolio, again, comprised of M and R, the risk-free asset. And then if I've got 70% of my wealth in R, then it's 0.7 times 0.1. And of course, that equals 7%, 0.07. And then 0.07 or 7% will be the standard deviation of the return of the portfolio of two securities. 7% will be the standard deviation of the return of the portfolio of two securities. In this case, the two securities are the risk-free security R and the risky security M. And so when you see something like this, think that it's going to graph as a straight line, and that is precisely what we had here. Now, something's interesting. Having made that point, let's go on to the next point. I'm going to choose a tangency point. A ray coming out of this point, just tangent to the efficient set. Okay. That's the best we can do. That's the steepest line we can get coming out of this vertical intercept. And what's very interesting about this line is that it makes clear that every portfolio on the blue line is now inferior to portfolios on the purple line in a vertical direction. You can see they're all inferior. Okay, and this means that this curve, I'll now highlight this curve in yellow. Okay, this line right there. Okay, is the best that we can do. It becomes the new efficient set. It is the new efficient set. Okay, this is the new efficient set. Okay, and because it shows the highest return given the level of risk that's possible. And so we have this line. The line ends there, but because we can short sell, but because we can do margin purchases, the line extends. So point R involves a weight in R of 1 and a weight in M of 0. Okay, that's portfolio R. Portfolio M involve if we're everything in M. If we're at R, that's everything in R. If we're at M, right there, we've got everything in M and nothing in R. Okay, but we could also be at this point right here, and that would be I'll call it L. L would be 0.5 here and 0.5 there. So the weights have to sum to 1, sum of the W's, right, of course, is 1, 1, 1. But let's consider a new point. Let's consider this point right here. Okay, it looks like that's about a weight in M of 1.4, and therefore the weight in R must be negative 0.4 because the weights have to sum to 1. And this example right here, involves margin purchase. Margin purchase. Okay, so this line has a name. I'm going to color this line now in, I guess we'll make it pink. And I know I'm changing the colors, that's okay. That pink line there has a name, and it's called the CML, or the capital market line, and it is comprised of efficient portfolios only efficient portfolios. Nothing else is on that line. No inefficient portfolios, no individual stocks. There's no such thing as an efficient single stock because a single stock has unique risk, non-market risk, firm-specific risk. Those three are synonymous. So that's the CML. All right, so that's a part of the theory that you should be aware of. I'm not a big fan of the idea, but that's okay. It doesn't matter what I'm a big fan of. Now, let's make an adjustment to this. In the real world, in the prior example, rather, we assumed you could borrow and lend at the same rate. That's ridiculous. So let's modify this a little bit. Here is the risk-free rate when we borrow. Here is the risk-free rate when we lend. Okay? So everything's different now when we consider that simple reality that risk-free borrowing rates and risk-free lending rates differ. In other words, when we lend money to the federal government, the rate that we earn is going to be less than the rate we pay if we borrow money to do something at a fixed rate. And so once again, if we have an efficient set right here, okay, and the idea is if I'm risk-free lending, that's relevant for kind of this area, okay, down here. In the graph, of course, I'm just drawing a circle down there. And so I'll look for a tangency point. It looks like it's about right there. And then I'll draw an orange line. Okay. And then change the color to red. And I'll draw a point of tangency there, which is going to be the tangency point from the vertical axis where we have risk-free borrowing rate. And that line is going to look like this. Okay, that line's going to look like that. Well, so what's going on here? Well, I want you to note that here we've got a whole bunch of risky portfolios, many of them. Portfolios, plural, yes, many portfolios, not just a single one. And the capital market line has an idea of just a market portfolio where you have market value weightings of all the stocks, all the investments, not even just stocks that exist in your own portfolio. You have market value weights for every asset that exists. Here we have theoretically an infinite number of portfolios along that curve, and then let's think what the efficient set looks like. Well, I'll draw it now in blue. Here's the efficient set. See, down here I'm borrowing, so this is relevant. Okay, then we've got this curve section, and then beyond this point, I'm here I am lending money to the federal government. I'm buying Treasury securities, and here I'm just investing in risky portfolios. And then from this red point on, I am borrowing money to invest in one of these portfolios. And so this becomes relevant. And so here's what's irrelevant now in yellow. That's irrelevant, and that's irrelevant. So what we're left with then is an efficient set that looks like this. Okay. Our efficient set, then we've got sigma r here, r bar here, looks like this. I'm going to make use of something here. Okay, and so this is going to look like this. And a curved line segment, and then a less steep straight segment. And there we go. And that's what the efficient set looks like when we consider different borrowing and lending rates for the risk-free side of our portfolio. And then this line becomes the real, oops, don't know what that was. This becomes the real, I'll put it in quotes, or the true efficient set. Investment possibilities that exist in the real world, combinations of risk and return that exist in the real world that you could choose to take positions in, and this is supportive of buy and hold investing, buy and hold. So this is supporting buy and hold investing. Okay, this is the theoretical underpinnings of that. And then this is your set. Now where you are, this is your opportunity set right here. And then where you are depends upon the nature of your indifference curves, right? So some people look like this. Some people have steeper ones and look like that. This guy will be here. This person will be there. And that is that. Thanks for watching.